Hi, I'm Sang-Jun Han. Today I'm going to talk about complex amplitude modulation with electronically tunable graphene plasmonic metamolecules, which is published in ACS Nano in 2020. Let's go into it. In this work, using the metamolecule, we achieved independent active tuning of amplitude and phase of mid-infrared light. And we found a physical model to describe these metasurfaces and proper design guidelines. And finally, we found that extreme wavefront control can be performed using these metasurfaces. Wavefront shaping is a crucial technique for holography, high-resolution imaging, optical twizzing, optical data storage, and communications. Especially if the wavefront in the mid-infrared region can be controlled, various technologies such as very thin lens, which can be mounted on a chip, a LiDAR, a memory device, or an active thermal hologram which creates a virtual heat source in space may be possible. The requirements of wavefront shaping in the mid-infrared region can be summarized as shown in this figure. When an incident wave approaches a specific optical system, the wavefront can be modulated to its desired form. If this optical system can achieve the three properties, it can be optimal wavefront shaper. The first is the electrical tunability. It is a technology necessary for real-time wavefront shaping without changing the original structure of the system. Second, the smaller or thinner the optical system, the better. If the device is miniaturized, it is easier to insert them into a smartphone or various devices. And if it is thin, it is easy to make them into flexible form. Third, a possibility to efficiently modulate the complex amplitude. Here, the complex amplitude is a word that expresses the amplitude and phase of the scattered light. If the amplitude of phase corresponding to this complex amplitude can be efficiently modulated, it means that the wavefront itself can be modulated efficiently, so it is actually the most important point to achieve. So, in order to approach these three properties, we utilize graphene plasmones. Graphene, as you all know, has exotic optical properties which can be exploited. Especially, plasmones in graphene are extremely small. The wavelengths of graphene plasmones is about 100 times smaller than that of free space light. So devices using graphene plasmones can be shrunken to sub-wavelength scales. Second, due to its carrier mobility, it is expected to have law loss. And thirdly, one of the most important characteristics is the electrical controllability. By applying electrical gate to graphene, its optical properties can be changed, so it is being used to develop various electrically adjustable optical systems. Thus, two of the three achievement points of wavefront shaping mentioned before, such as electrical tunability and compact size, are already resolved. So in this study, I would like to introduce the third achievement, the process and results of designing a modulator that can efficiently and electrically modulate complex amplitudes. Light modulators that have been studied in this field were able to modulate only the amplitude or phase. Or, even if all the complex amplitudes can be tunable, it was hard to obtain dynamic or time-varying wavefronts because it was passive metasurfaces. In this study, we utilized graphene modulator to resolve these limitations. However, there were also problems. The first problem is, due to extremely small size of the graphene plasmon, they hardly interact with the free space light. In previous cases, the modulation efficiency are less than 10%, which is not practically useful. In order to achieve high absorption efficiency, the absorption cross-section of one device is theoretically expected that it should be much larger than its physical area. But due to low mobility and fabrication imperfection of graphene, conventional graphene plasmonic devices have poor absorption cross-section, which is even smaller than its physical area. Thus, we need mechanism to enhance the modulation efficiency even with poor quality of graphene. The first option is using a dielectric resonance. In this work, we attached a dielectric resonator, which is composed of silicon nitride and gold reflector beneath the graphene nanoresonator. In the experiment, we measure the absorption modulation spectra by spatially and spectrally overlapping the resonance of dielectric resonator and graphene nanoresonators. The modulation efficiency substantially increased to 25%. And another enhancement mechanism is exploring the resonant metallic slit. In this experiment, noble metal plasmonic resonance overlap with the graphene rebound resonance, so there is a 2.7-fold transmission enhancement over bare graphene rebounds. We combine these enhancement mechanisms to a single device, so we can expect that these result in a huge modulation enhancement. As you can see, this E-field intensity profile, which is calculated with FDTD simulations, it increases drastically when we introduce this resonance overlapping. And the absorption spectra also can be enhanced in combined structure. And for a specific Fermi energy of the graphene, we confirm that perfect absorption can also be achieved. So we experimentally demonstrate the perfect absorption using this resonance overlapping. On silicon oxide and silicon nitride substrate, we added two enhancement mechanisms that were mentioned before and measured absorption spectrum. This absorption spectrum is a function of graphene Fermi level and frequency. So as you can see here, up to 96% modulation efficiency can be achieved even with poor quality of graphene. So we could demonstrate efficient active amplitude modulation. But in order to achieve active complex amplitude modulation with conventional resonance structures that have a single tuning parameter, due to inevitable correlation between amplitude and phase, the independent control of phase and amplitude was impossible. The same problem usually occurs because metasurfaces are constructed using only meta-atoms with a single resonance. In this study, metamolecules were constructed instead by combining two meta-atoms with a single resonance, and metasurfaces were created using this new type building block. The properties of the metamolecule are determined by the Fermi level of the graphene that constitute it. Previously, there was only one type of graphene Fermi level that could be changed. Now that there are two, the degree of freedom to be adjusted is increased, and finally, the amplitude and phase can be independently modulated. The performance of the metasurfaces using metamolecules can be expressed in this figure. This red dotted line refers to a line with the same complex amplitude of reflectivity. And this single point means this wavefront. You can see that the wavefront is gradually dragging while maintaining the reflection amplitude along this line. Likewise, along this blue line, the reflection phase is constant, but reflection amplitude are varying. All the simulations was done at graphene mobility of 1000, which is sufficiently achievable in the real fabrication process. But even assuming a poor quality graphene, we can achieve the complex amplitude modulation. And of course, at higher mobility, we can get a much wider area. And here, a purple area is the area when the Fermi level is changed from 0 to 1 electron volt. In fact, 1 electron volt is the condition that is difficult to achieve in real-world situations. However, if you check the green area, which means that the maximum Fermi level is decreased to 0.6 electron volt, you can see that complex amplitude modulation still occurs. Now I will explain the design process to determine the structural parameters of these metamolecules. In this process, many arc graphs will appear, which is in the same context as the trajectory drawn by meta-atoms when describing the performance of metamolecules previously. The optical response of the meta-atom with a general resonance has a Lorentzian shape as a function of the Fermi level. When this Lorentzian shape moves to a complex plane, it will show circular shape. So in the following explanation, I will explain the design principle with these arcs. This arc gets closer to a complete circle as the Fermi level range goes extended. Since the metamolecule should cover as many complex amplitude points in the complex plane as possible, designing the structural variables to make this green area wider is the first design goal. And another criterion can be to design the green area to have a largest inscribed circle as possible, because these concentric circle lines are the lines where only the phase can be changed while maintaining the amplitude, and it can be useful later for wavefront shaping. The detailed design process is as follows. Because there are too many kinds of structural variables that metamolecules have, to design metamolecules right away, breaking them down into meta-atoms is the first step. After that, meta-atoms are optimizing according to the above design criteria, and the optimized meta-atoms are recombined to obtain metamolecule properties. In this process, it is important to find the equation between metamolecules and meta-atoms, and the optimization process of meta-atoms is also important. So I will explain this process one by one. First, the process of finding the relationship between metamolecules and meta-atoms are important. In the existing complex reflectivity plane, the relationship between the metamolecules and meta-atoms is quite ambiguous, and it is difficult to estimate which meta-atoms are needed to create an optimized metamolecule region of this combination. It means the relationship between R1 and R2 and R total is not intuitive. So we introduce the effective admittance model. In the effective admittance model, a multi-scale structure is modeled as a stack of material with some effective admittance. Admittance is a value having the reciprocal value of impedance, and the effective admittance of the material can be thought as a concept similar to the surface conductivity of that material. And this effective admittance has relationship with the complex effectivity that we were originally interested in. Also, as one of the good properties of this, the admittance also has a Lorentzian shape, so it has a circular shape on the complex plane, and we can discuss the same things as the reflectivity. Then, the advantage of admittance compared to reflectivity is that admittance can lead to the relationship between meta-atoms and metamolecules. This is because admittance has properties similar to surface conductivity, so the connection of the admittance can be thought as a series connection of circuit elements. Therefore, it is now possible to optimize meta-atoms individually without having to directly optimize metamolecule itself. And looking at the complex admittance plane, this reflectivity region will transform to this admittance region, and the origin will move here to there. So now you should find two specific meta-atomic admittance lines and design them to become those green area, which means metamolecular admittance area. So in order to find proper meta-atoms, there are several things to consider. First, the admittance of the substrate must be considered. When looking at the case of A and C, which is the case where the imaginary part of the admittance of the substrate is different from the imaginary part of the meta-atom, and the case of B, they are canceling out with each other, you can see that the covering area of in the R plane is the largest for the B. Therefore, this meta-atom must be designed so that its imaginary part of admittance is same as that of the substrate. In the admittance of the meta-atom, periods and gaps between the metal strips are the main parameters. As you can see from this graph, if the period widens while the gaps between metal strips is fixed, the metal widens and the structure becomes more capacitive. So this admittance circles goes down. And the radius of the admittance gets bigger since periods over gaps gets bigger. And as gaps grows, it becomes less capacitive, so admittance circles rise higher and the radius becomes smaller because P over G becomes smaller. After finding proper meta-atoms, you can connect the design two types of the meta-atoms with this equation, which means the relationship between meta-atoms and metamolecules. So numerous fine-tuning candidates can be obtained, and you can select the best metamolecule option. Using this optimal metamolecule, the amplitude and phase of the affected wave can be independently controlled, so the original purpose of the wavefront control can also be performed. The detailed wavefront control process is as follows. It goes through a process similar to recording and reproducing process of a hologram. If the metamolecules at each location produce the appropriate complex amplitude, the desired wavefront can be created. So we can try beam steering with this principle. It was designed so that all metamolecules have the same amplitude, 0.5, but the phases are different from each other, and confirmed by simulation that vertically incident light can be steered to 72 degrees. And beam focusing can also be performed using a similar principle. If the amplitude of the metamolecule at each location is lined this way, the clear focus can be achieved at a location only one wavelength away from the metasurface, and it is also possible to implement triple foci with higher spatial resolution, which are several wavelengths apart from it with each other. If you can control the amplitude and phase independently, you can get a cleaner wavefront than otherwise. If you do not care about the amplitude in a way that is commonly used in the phase hologram, you will get less clean wavefronts as you can see in this figure. So this is the end of the presentation. If you have any question, please contact this email. Thank you.